30 years ago, the first solar cells were made of silicon, and today silicon makes up more than 3/4 of the rapidly growing worldwide photovoltaic market. But photovoltaic, or PV cells, are also made with other semiconductor materials. Why so many types of solar cells? This diversity is due to innovation. PV materials are improving, manufacturing costs are dropping, and PV applications are expanding. Balancing these three factors can meet demands for clean green power while creating more American jobs. Innovation means improving photovoltaic materials. Every PV material absorbs sunlight differently depending on band gap, which is a unique electronic property of the material. Some cells absorb sunlight within the first micron of material. Others need 100 times more material to absorb the same amount of energy from the sun. The sun's energy arrives as a combined spectrum of different wavelengths. Each color carries a different amount of energy. This makes solar cell design more complex. If the energy of the absorbed photon matches the PV material's band gap, then an electron-hole pair is created. If the photon has more energy, it still creates only one electron-hole pair, but the additional energy is lost as heat. If the photon has less energy than the band gap, it is not absorbed. Low band gap materials absorb most of the solar spectrum, creating many electron-hole pairs, producing a high current. However, PV cells with low band gap materials have a low voltage. High band gap materials absorb only higher energy photons, creating fewer electron-hole pairs, producing a lower current with a higher voltage. A solar cell's efficiency is the percentage of the solar energy shining on the cell that is converted into electrical energy. One way to increase efficiency is to use multiple layers to capture power from multiple wavelengths of light. Understanding the properties of each PV material allows scientists to improve designs that maximize the power of the cell. Innovation in PV also means lowering the cost of manufacturing. Crystalline silicon cells have high efficiency because they use very pure single crystalline silicon, which is expensive to manufacture. Multicrystalline silicon cells have lower efficiency, but they can be cheaper to manufacture because they use lower quality silicon, less energy, and simpler manufacturing equipment. Thin film solar cells can be made from materials such as cadmium telluride, copper indium diselenide, or amorphous silicon. These materials absorb light more readily than crystalline silicon, so they can be used in very thin layers that are less expensive to produce. Thin film solar cells are generally less efficient than crystalline silicon cells, but they can be cheaper to manufacture because they use less semiconductor materials, which are grown on glass or flexible foil. Finally, innovation means meeting different applications best suited by different types of solar cells. Today, PV devices produce power to meet the needs of utilities, businesses, homes, and consumer products. Large-scale installations can use a range of highly reliable PV technologies. Solar-powered satellites are more sensitive to power per pound. These high-efficiency solar devices can accept higher material and manufacturing costs to get more electricity from less material. Flexible thin-film devices are being installed in innovative ways, including incorporation into structures with complex shapes. Photovoltaics are here and now, and the diversity of PV devices is advancing as scientists improve PV materials and develop new manufacturing methods. More solar applications are emerging as these innovations make PV more affordable.